Okay, let's get started. It is my great pleasure to introduce today's speaker, Professor Mike Widom. Mike received his PhD in physics from University of Chicago in 1983. After spending 2 years as a postdoc in Harvard University, he joined the faculty of Carnegie Mellon University in 1985. Mike is American Physical Society Fellow and the AAAS Fellow. His research includes quasicrystals, amorphous metals, and the metallic alloys. Let's welcome Mike.
Okay, great. Thank you very much, Yang. So I had promised to give a talk about generalizations to mean field theory, and I'm going to speak specifically about what's known as the cluster variation method. This is now a 70-year-old topic that was pioneered by Ryoji Kikuchi, who used it to study models of statistical mechanics. And also its generalizations to alloys. And so I'm going to tell you about the basic principles and also its application to alloys, in particular high entropy alloys. So since it's a generalization of mean field theory, I'm going to start by just reminding you about sort of undergraduate level mean field theory, which I will point out is a sort of the initial step in a sequence of approximations that constitute the cluster variation method. So let's go to the standard nearest neighbor Ising model. Here's the Hamiltonian written with spin sigma plus or minus 1, assuming nearest neighbor interactions. Yeah, so I'm also going to introduce an alternate spin representation, which is the magnetization, which is the mean value of the spin. Okay, so in terms of this mean value of the spin, we can write the energy as minus j, the coordination number divided by 2. That's because the number of bonds per site is 1/2 of the coordination number times the square of the magnetization. Why is that? Well, that's because if we focus on a particular spin sigma I and then sum over its neighbors, the sum of its neighbors is then going to be the number of bonds times the mean value of the spin, which is this magnetization. Okay, so, and then when you sum over all the spins I, that gives a factor of the number of spins n, take per spin, and we get this energy, which is minus j, the number of bonds per spin times the square of the magnetization. So that's the mean energy, and I've already introduced now the mean field, which is the magnetization. But we also need a representation for the entropy. So the entropy per spin, per site, will be the log of the number of configurations. And this log of the number of configurations we can also identify as the Shannon information required to specify specifically what is the value of each and every one of these spins. That's because log of omega is minus log of 1/omega, and 1/omega is the probability for a particular spin configuration. If we have omega configurations, 1/omega is the probability for any one of them, at least assuming the absence of any particular order. Okay, so how are we going to write down an expression for this entropy? It's not obvious immediately how to do it. In particular, we want to express the entropy in terms of the mean field M. So how do we do that? Well, let's write the mean field M in this form, where I've introduced a new variable x, which is 1/2 of 1 plus m. The nice thing about this new variable x is that it ranges between 0 and 1. And there's a nice symmetry between the value of x and the value of 1 minus x. So now let's use that new variable x to write down the number of configurations for n spins subject to a mean magnetization m, which I rewrite in terms of this variable x. So now we know that we want xn up spins, and the remainder, which is 1 minus x times n, that many down spins. And we know that that can be written in terms of a binomial coefficient, where we just ask how many combinations are there out of a total of n spins, how many ways are there to make xn of them point up. Of course, this binomial coefficient is n factorial divided by xn factorial times 1 minus xn factorial. And then we take those factorials, the ratio of n factorial divided by these xn factorial factors, apply the Stirling expansion for the factorial to write it as xn log xn minus minus xn. Turns out that all the xn factors cancel against each other, and we're only left with the x factors. And when we look at the entropy per spin, we are left with an minus x log x from the xn factorial, and a 1 minus x log 1 minus x from the 1 minus x n factorial. Okay, so that's the entropy that we see that we can rewrite in terms of this variable x. Of course, we would like to rewrite it in terms of our mean field variable m. And so we then, substitute x is a half of 1 plus m, 1 minus x is a half of 1 minus m, and we end up with this expression for the entropy, together with this expression we already had for the energy, and that gives us the free energy. Then we want to find the condition for equilibrium. In the condition for equilibrium, the mean field, which is the global magnetization, should minimize the free energy. So we set the derivative of f with respect to m equal to 0. Differentiating the energy, we get this term that involves the coupling constant J. And differentiating the entropy, we get this expression, which turns out to be a representation of the inverse hyperbolic tangent function. And so substituting that inverse hyperbolic tangent, then we get this familiar looking expression, which is the way that mean field theory, at least in my undergraduate stat mech course, that is the conventional way of representing the mean field theory self-consistent condition. Okay, so how do we solve this self-consistent condition? The way that we do it in the undergraduate class is a graphical approach. So we make a graph of the left-hand side of the equation, which is the equation m prime equals m. And then we graph the right-hand side of the equation. So here's this hyperbolic tangent. And then we look for intersections, and we find there is always an intersection at m equals 0, corresponding to the disordered case. But if the temperature is sufficiently low or the coupling constant sufficiently high, then the slope of the hyperbolic tangent exceeds 1, and we find an additional pair of solutions that actually are lower in free energy than the solution at 0. And so those are the proper solutions. And so if we were to graph the stable solution as a function of temperature, we would find at high temperature, where the slope of the hyperbolic tangent is low, we only have the solution m equals 0. At low temperature, we get these other solutions with the characteristic square root singularity that demonstrates to us we are doing some type of mean field theory, and we are not taking into account all of the possible fluctuations. The critical temperature here occurs at the coupling constant times the coordination number. But there's an alternate way of solving the problem. So we want the solution that says m is the hyperbolic tangent of itself. Well, we can also solve that through an iteration method, which people familiar with doing first principles methods might be familiar with. It's the same kind of method you might use to solve the self-consistent electronic structure problem. But here we're solving for the magnetization instead. So we randomly choose some magnetization. Let's say we choose this one here. We choose this magnetization. We go up to the value of the hyperbolic tangent and project over to m prime. That will give us a magnetization somewhere around here. We go back to the hyperbolic tangent, find the new m prime, and we will quickly converge to this value. If we had started with a value below the equilibrium value, going up to the function would increase the value. So from either side, we converge to the correct value. Okay, that's conventional mean field theory. But now we want to do a little bit better. We would like to include some degree of fluctuations, but these fluctuations are not completely random. There are correlations. So for instance, if we know that one spin is up, and if the coupling constant J were positive, then it's quite likely that the nearest neighbor spin would also be up. And we can actually use that to rewrite exactly the value of the energy. So here I'm introducing the near neighbor pair frequency function y sigma sigma prime, where sigma prime is just the value of the spin that is the neighbor of sigma. And let's go back to this, this energy here. So for a given spin sigma, we need to sum over its neighbors sigma prime. So sigma I is sigma, sigma j is sigma prime. And we need to sum over all of its neighbors. Well, what are the values of the neighboring spins? They are correlated in some way with the value of sigma, and that correlation is encoded in y sigma prime. So z over 2 times y sigma prime, that is the sum over the neighbors of sigma, but we still have to sum over sigma. Well, that's true. So y sigma sigma gives us the value of sigma when it's equal to, gives us the value of sigma prime when it's equal to sigma. But sometimes sigma prime will be the negative of sigma. So here, sigma bar is the negative of sigma. And so we have to subtract those cases where they point in opposite directions. So this is now an exact formula for the energy. So we are no longer making an approximation for the energy, but we do have to make some approximation for the entropy again. So how are we going to calculate the entropy? Well, again, we're going to distribute n x sub sigma spin sigma out of n spins. And so that will give us our minus x log x minus 1 minus x log x entropy as before, except that we have to distribute them subject to this constraint. And how are we going to put in this constraint? It's really unobvious, but Kikuchi came up with a clever trick that lets you do it in one dimension without approximation. And so what is his method? His method is to consider an ensemble of many spins. And in that ensemble of many spins, let's assume there are n-1 spins in this one-dimensional chain, an ensemble of many chains of spins. Here in the first chain, it happens to end with a plus sign. Then there are going to be many spins that end with plus signs. And here's another one that ends in a plus sign. And again, there are going to be many more. But here is the first one that ends with a minus sign, and another one that ends with a minus sign. Now, this first group that ends with plus, it just so happens that the next spin is also a plus. So how many are there in this group? Well, how many there are in that group is y plus plus times L, because y plus plus means that this spin is plus and that spin is plus. How many are in the next group? Well, the next group ended in plus, but then went on to minus, so they're y plus minus there, and so on and so forth. And then if you work out the combinatorial factors to count how many cases there are, you end up with these factors. So what is the total entropy? The total entropy is the product of those combinatorial factors raised to the n spins. By the way, I should say that this combinatorial factor is how many ways you can add a plus or minus spin to a plus sign. And this one is how many ways you can add a plus or minus spin following a minus spin. Okay, so this is going, these factors go just one step, like this step here or that step there. Okay, so this is how many ways to go a single step. We want to go n steps, but we have L chains, so there are L times n spins in total. So that's the entropy. And if you work it out, this is what you get. You get something that looks familiar from the original, what you might call entropy of mixing or Bragg-Williams entropy, except perversely, it has a plus sign, not a minus sign. And then we have another term that comes in here that involves these correlation functions. So this derivation relied on a trick. It's not at all obvious how you might generalize it. And maybe we lacked a little bit of intuition as to why it is specifically this formula. But I'm going to rewrite it in a way that tells us immediately why this is the correct formula and gives us a route to approximate generalizations. And so what I'm going to do is I'm going to take this expression that looked familiar but had the wrong sign, and I'm going to get rid of it because I didn't like it. But if I get rid of it, I'd better also add it back again, right? So I'm going to add 0, and I'm going to add 0 in this funny form. Well, I've subtracted it, so let me keep the term that I subtracted, which is right here. But then I added in this extra term, and we still have to account for this one. Well, these have positive logarithms in them. If they have positive logarithms, then I could rewrite them in terms of minus the log of 1 over x. And let me take all those minus 1 over x's and write them here as log of 1 over x. There are various other useful identities that I can invoke. For instance, x sigma is the sum over sigma prime of y sigma sigma prime. I'm going to use that identity to include this y sigma sigma prime form here. And now we end up with this form, which I claim has a nice intuitive meaning. So first, let's look at this one. This is the ideal entropy of mixing of the spins. It's also the so-called Bragg-Williams entropy for a binary, well, for any multi-component alloy. What is this second term? Well, it has a minus sign, so we're subtracting something. And so what is the something that we are subtracting? What we are subtracting is a quantity known as the mutual information content of the pair correlation function that describes the correlations between the distributions of spins sigma and sigma prime. And that mutual information content is a non-negative definite quantity. And how are we to think about this? Well, I already told you that this term is the Shannon entropy required to describe the specific configuration of a random assortment of spins. But now we recognize that there's an additional constraint. We don't have a completely random distribution. We have a random distribution subject to a correlation. And so we now want to remove the information required to account for the correlations between the spins and their neighbors. And so we have an uncorrelated information minus the mutual information of the distribution function. So think of this as sort of the total information required to specify the distribution. Because if we specified where most of the spins were, and we knew the correlation function, then without any further information, we could fill in all the remaining spins. And so there's this idea that there's an equivalence between thermodynamic entropy and Shannon information. And that's what I'm using here. Here we have thermodynamic entropy. Here we have Shannon information. Notice, by the way, that all of my entropies are in units of K Boltzmann. Okay, so that's the idea here. And this pair model, it's exact in one dimension, but we can also generalize it. So in one dimension, every spin has 2 bonds. But if we have a lattice of coordination number Z, we can generalize it in this form, multiplying by the correlation number divided by 2.
So, Mike, before you go on, let me ask you. So, it's well known that in 1D there is no phase transition. So,
yes,
is this
that mean field theory? Mean field theory does predict a phase transition even in one dimension, and so so mean field theory is not exact, except it works exactly in one dimension. And here it works, this generalization is a mean field theory. It is again exact in one dimension. It is a generalized mean field theory.
So sorry, I didn't understand. So this expression above, the previous expression on the previous page that you just showed, you said that these y's are calculated exactly in one dimension. So does that mean that
yes,
if you actually use this,
I have to specify here the entropy is exact in one dimension, but the mean field energy So here's the exact energy.
Yeah.
But this mean field energy is not exact.
Right. But is
In
there
any dimension.
Is the what I'm confused about is that it seems that the expression for the energy in terms of the y's, that was exact, right?
That is an exact energy of a single spin, but yeah. So let me clarify. Without the sum over, so if we had a sum over spins sigma I, this would be exact. But if here we just have a sum over values of the spin equal to plus or minus 1, that is then an approximation for the energy of the total. Yeah. So thank you for that.
So just to clarify, so even though the calculation of the y's was done exactly in one dimension, but the final expression for the free energy will not be exact in one dimension, right?
That's correct. The final free energy is not exact.
Because that's a very dramatic difference. I know that mean field theories will always give you a transition, but in one dimension there is no transition. And I was wondering whether it's possible. For example, I know that there is a beta Kikuchi, the beta piles approximation, which as it happens, I think actually is exact on the beta lattice, and the version of the beta, the 1D is actually a particular version of the beta lattice, and that will not have a transition in 1D.
So please look at this. And so, so the expression for the entropy, as I say, is exact in one. The entropy expression is also exact on any loop-free lattice. And examples would be the Cayley tree or the lattice, exactly as you're pointing out. Okay. And now I'd like to introduce some peculiar notation that is used in this field of the cluster variation method. So as always, the entropy is going to be the log of this omega. How are we going to write omega? I'm going to write the numbers of configurations omega in terms of products of functions that I call f. And there is a function f associated with single points. There's a function f associated with pairs. And you'll see that there are functions f associated with other clusters as well. What is the function f? The function f is the ratio of 1 divided by point. 1 is here to kind of keep the units right. And what is point? Point is the product over sigma equal plus or minus 1 of the factorial of x sigma n. Well, if we have 1 divided by this product of factorials, we have way too many n factorials in the denominator, and we need to fix it up with an n factorial in the numerator. That's why there's this 1 here. Okay, so what is omega point? It is 1 over dot. And how do we know that? Well, if we take the logarithm of 1 over dot, we end up with, taking the Stirling approximation for these factorials, we end up with minus x log x minus 1 minus x log 1 minus x. Okay, so this is omega point, and it gives the Bragg-Williams entropy, random entropy of mixing. What is omega pair? So for omega pair, we need to get this expression. Well, omega pair is f point times f to the power z over 2 f pair. And what is f pair? F pair is a product over y sigma sigma prime n factorials. And why do we raise it to the power z over 2? That's because every point has z over 2 pairs. And when we take the log, we're going to get z over 2 log of f pair. Notice, by the way, that f pair also, well, f pair has this bracket pair factorial factor. But remember that every pair comes along with 2 points. And we don't want to overcount the points. So we have to remove the points from the pairs. And so I take the 2 points that come with every pair and I put them in the numerator. It's very much like here we had pairs in the numerator, and then I had to remove them by placing their frequencies in the denominator. So we have 2 points in the numerator, 1 pair in the denominator. Well, now we've got too many factors in the numerator, so we have to correct it with this extra 1 factor in the denominator. So I hope that you see there's some intuition to how these factors are assembled. And it also has a very nice information theoretic notion that comes from the so-called inclusion-exclusion principle.
So before you go on, Mike, can I just ask, the mean field theory, the usual simple one, is exactly when you have an infinite coordination number. Now, are these terms that you expand, there's more and more higher order terms, are they ordered by some like 1 over z, or is there a small parameter that will control their?
Yes, there is, and I'll try to point that out later when I explain how the whole CVM is a type of cumulant expansion in successively larger objects that contribute less and less to the entropy. So keeping in mind this equivalence between the Shannon information and the thermodynamic entropy, what we want to do is we want to account for all of the information. So let's say that we have a certain amount of information contained in the set A, and some other amount of information in B, and some amount in C. Okay, so here we have this collection of sets. But if we want to look at the total amount of information present, well, if we were just to add up the individual pieces separately, we would have overcounted, because here, shaded in green, are pieces of information that are shared in common between the set A and the set B. So we'd better remove the intersection of A with B, also B with C, and also A with C. But then we would see that this region here in the center, it's been included 3 times, way too many times, but then we removed it 3 times again. And so that we see we have to include it 1 more time. And so here it is added back in. Okay, and notice that there's this funny alternation in sign, where if we have 1 object, it comes in with a plus sign. If we have 2, it comes in with a minus sign. If we have 3, it comes in again with a plus sign. And if we had, 2 identical copies of B, well, then we would probably have to, put some interesting factors in here in order to make things absolutely correct. So there's going to be some funny algebraic rule for carrying out this calculation. And then let's say that we had information contained in points, and we had information contained in pairs, information contained maybe in triangles, for example. Well, every one of these clusters would have associated with it a certain amount of entropy associated with the frequency with which it occurs, decorated by certain values of the spins. So for instance, for a point, rho for a point is just the function x sigma, x plus, it has values x plus and x minus. Okay, but let's think about a triangle. The triangle contains pairs and it contains points. And we somehow had better remove the part of the triangle that we would like to attribute to points and pairs, because I want the point to be my dominant contribution, the pair to be a small correction, and the triangles to be an even smaller correction. So to make that happen, we need to carry out this, this cumulant expansion. So I'm going to say that the total entropy is a sum of cumulants of the entropy. But what is the cumulant of the entropy? Well, for a given cluster alpha, we want to remove all of its subclusters, but some of the subclusters will be, 1 point smaller than the cluster itself. So we want this factor -1 to the +1, like a point is 1 point smaller than a pair, but a point is 2 points smaller than a triangle. So if we have the cluster alpha being a triangle and the subclusters being points, well, then we'd better add that term back in. And so here we are adding it back in because we have -1 to the power 2. Okay, so these are the cumulants of the entropy calculated using the inclusion-exclusion formula, which in this case is known as a Möbius inversion formula. And the idea is that while the cluster entropies, they are kind of, the cluster entropies, let's say they are of order the size of the cluster, but the cumulants are in general much smaller than the size of the cluster. So we then have the total entropy written in terms of a series of decreasing magnitude that we might hope would converge. Okay, let's work this out for another case. So let's do the Kramers-Wannier approximation for the square lattice. So a square has near neighbor bonds. They come in two sorts, horizontal and vertical. And there are 2 such bonds per site. There are also triangles. So here, for example, is a triangle. And here's another triangle. There are 4 such triangles per site. There also are these long bonds contained within a square and the square itself. So here I write down the factors for, the long bond and the triangle, and here is the factor for the square. Let's think about it. The square comes in the denominator because the object itself is always in the denominator. We have to remove the 4 triangles, but we also have to, after we remove the triangles, we have to add back in the short bonds and long bonds. And then we have to correct for all the points, and we have to make sure the units are correct. And then we write down the omega for the square, which is a product of all of these things raised to the appropriate powers. And then we end up with this nice compact formula. And finally, this is the entropy for a square. We could also do it for a body-centered cubic lattice. So here's a body-centered cubic lattice. And we've already looked at all of these objects. The only new thing is this 4-point cluster, the body-centered cubic irregular tetrahedron. And so here is the formula for the tetrahedron, first worked out by Ackerman, Inden, and Kikuchi. And I'd like to call your attention to the fact that the body-centered cubic lattice has 4 sublattices that I label alpha, beta, gamma, and delta. And we can also think of 2 sublattices, like the even sublattices that sit at the vertices of the cube and the odd sublattice that sits at the body center. Then we have nearest neighbor frequencies for every pair of sublattice. Next nearest neighbor frequencies, triangles, and tetrahedra. And there are a variety of identities, like if you take the tetrahedron and sum over these spins, then what you are left with is this triangle. Okay, so there are a variety of identities, including overall normalization. And there's an interesting hierarchy of ordering. So the hierarchy of ordering involves what's known as the set of Heisler structures. The most general of these is the quaternary Heisler, quaternary because there are 4 sublattices, and then we place different chemical species, red, blue, yellow, and orange on each of these different sublattices. That structure actually does occur in a variety of lithium-based quaternaries. Then if we had, for example, chemical disorder on 2 of the sublattices, so if we had random mixing of the red and blue, then we could replace all the red and blue atoms with purple. And then we would have what's known as the full Heisler structure, which is aluminum, copper, 2 manganese. We could instead average, let's see, we are averaging the red and the orange. Let's see, sorry. We are averaging the blue and the orange. And the average of blue and orange, I've written here as brown. That's kind of like the full Heisler, but it's different. And so they call it the inverse Heisler. We could leave we could leave 1 sublattice vacant, and they call that a half Heisler, even though they should call it a quarter Heisler. And then here are 2 other structures that are both binary alloys, the sodium thallium and bismuth trifluoride structures. And then finally, we have cesium chloride. Cesium chloride is like chemical order on a body-centered cubic lattice. So we have disorder among the vertex sites and also disorder among the body-centered sites, but the vertex and body centers retain distinct average chemical identity. And then finally, we would have complete disorder, every site occupied equally. That would be the tungsten prototype. Cesium chloride is sometimes called a B2 structure. The tungsten prototype is sometimes called A2. This is structure Bericht notation, a terrible notation that unfortunately is popular in the material science community. And also this sodium thallium is known as the B32 structure. There is almost no rhyme or reason to the naming of these structures. And in the Ackerman paper, they assigned various energy interactions to the to the different nearest and next nearest neighbor pairs. And then they looked as a function of temperature and concentration, looking only here at binaries. They looked at different phase diagrams. And you see, well, at high temperature, you always get the fully disordered BCC structure. As temperature goes down, if you are equiatomic, then you tend to get the B2 structure, unless there is a certain sign of relative interaction, in which case I think it's maybe if the next nearest neighbor interactions favor, I don't know, there's a certain constraint on relative signs and magnitudes that you can look up in one of my papers I will cite at the very end, that favors this B32 sodium thallium structure. Okay, so they find a variety of different phase diagrams, always being BCC at high temperature, but then different structures at lower.
So Mike, can you say, it seems that from my reading here, they've actually checked this against Monte Carlo, but what is the level of the variational theory that they have to use?
Well, this was done using the tetrahedron model. I actually think you can get all of this at the pair level, but they didn't. They used the tetrahedron model. Okay.
So it seems pretty accurate.
Yes. And then thank you for mentioning Monte Carlo. And so I've had a series of projects with undergraduates over the years that involve the combination of Monte Carlo and cluster variation method. And so one idea is to use Monte Carlo to generate the correlation functions, and then use the correlation functions to evaluate the entropy within the cluster variation method. And the Monte Carlo, you can either do very efficiently with model Hamiltonians, possibly fit to first principles, or you can do it purely from first principles, in which case it's rather slow. Okay, so what I'm showing you here are figures from work by Drew Kim, CMU senior, that show the result of simulations that show the point occupation for binary molybdenum tantalum as a function of temperature. So we have high temperature and low temperature on the alpha sublattice. And as the system size grows at high temperatures, the concentrations converge towards 50-50, but below TC, they converge to a very steeply varying concentration with a critical exponent of 1/8. 1/8 because it's an Ising model.
So is this rounded because of finite size effects? I mean, it doesn't.
It's rounded because of finite size effects, exactly.
Okay.
So these are the point occupations, and here I show the normalized pair correlations. And notice this very large, pair correlation function for the molybdenum tantalum pair. But notice also that those pair correlations, we haven't shown the finite size sequence, but in fact, it converges towards this function here, where the normalized pair correlation exceeds 1. 1 would be the uncorrelated expectation, even above TC. And that's because even above TC, although we have global disorder, we still have short-range disorder. And that short-range disorder is going to, we have short-range order. And that short-range order is going to give pair correlations. And now if we look at the entropy within the cluster variation method, taking the simulated correlation functions, we see at the point level the entropy is systematically equal to the log of 2 above TC, and then below TC it drops off due to the due to creating the sublattice order. But if we look at the entropy at the pair level, so the nearest neighbor pair is shown here in green. Notice how low the entropy is at the pair level. The entropy is so low at the pair level because we have these nearest neighbor correlations. And then if we include the next nearest neighbors, it gets even lower. If we include the triangles, it goes up by quite a bit. But then if we go to the tetrahedron level, it's in pink, and it's hidden here right below gray, where gray labeled here as histogram. It's the result from evaluated directly from the Monte Carlo. So we see a kind of convergence where the next nearest neighbors underestimate the entropy, 3-point functions overestimate, and the 4-point function is essentially exact. That's for the binary. And over here, we see essentially the same thing for the quaternary. And so this raises some questions about the nature of convergence in the cluster variation method. So Drew, Kim, and I carried out a high temperature series expansion for the body-centered cubic Ising model. And here are the first 3 terms in the expansion of the exact entropy in powers of coupling constant over KT. Okay, so J over KT to the 0, to the 2, to the 4, and so on. So we have log 2 minus twice the quadratic term, minus 35 times the 4th order term. And then we carried out the series expansions for the correlation functions and stuck them into the cluster variation method. And so we see that for all variants of the cluster variation method, well, I should say the point approximation will only have the log 2. But then for all the higher approximations, we always get the correct 2nd order term, but we always get the wrong 4th order term until we go to the tetrahedron approximation.
And that's because you have the four sites.
And that's, of course, because we have the 4 sites. Now, there were some choices we could have made about the 4 sites. Like, instead of taking this tetrahedron, we could have taken this triangle, and then we could have added a 3rd neighbor. That would have been a bad idea.
Right.
So there is a notion that we should always use the most compact cluster. Okay, but the Monte Carlo simulations, those were done using a model Hamiltonian fit to first principles data. And so we could also use that model Hamiltonian to run the cluster variation method. I think I have written down here somewhere the iteration formula. Well, I guess I don't. But yeah, there is a nice iteration formula for the, oh yeah, here it is. Here is the iteration formula for the 4-point correlation function within the cluster variation method. There is an issue about how to maintain constant concentration. You have to introduce feedback on the chemical potentials. And if you do that, you end up being able to run the cluster variation method and calculate these same site occupation and correlation functions. Here for the, here we have the single points for an Ising model for the MOTA binary. Here we have pair correlations for MOTA, and for the high entropy alloy, the single site occupation. These things were done by Peter Winstel, a current undergrad. And then I'd just like to finish up by showing references, and I've exactly used up the available time, and but I'm happy to take questions.
Oh, that's a great talk, Mike. And you use time very wisely. That's nice.
Thank you,
So
yeah.
So any questions?
I think Vlad has a question.
Okay.
No, this is, I'm just applauding. This is
Oh, that's applause. Okay.
Clapping.
Mike, I'll make a comment or give my, you know, the angle that I'm going on. So if you were to do Monte Carlo and get the correlations, well, then the entropy is just some functional of that correlation. You've shown how to do it as various approximations in CVM, but you could say, okay, well, CVM is pretty good. Let's go and cook up something that's a better functional.
Yeah.
Have you thought about going along those directions?
No. So I guess I kind of like series expansions. So you saw that I like the high temperature series. You also saw that I like the cumulant expansion. And so, yeah, I look to make things that are, you know, in principle, systematically improvable, and where I think I know how to, you know, make estimates of errors and so on.
In the cumulant expansion, it looks like you were running into some ambiguity, though. That's the convergence of that expansion is not guaranteed, right? Or maybe the status has changed since I looked at it last.
Yeah. I think in terms of rigorous mathematical proof, I actually don't know the current status. But I think that I've through experiments like this one. By the way, this inset here, that shows the difference between the CVM and the Monte Carlo. And so you see here the pairs are low and quite a bit low. Here the triangle is a little bit high. Sorry, the point is very high. The pairs are somewhat low. The triangle is a little bit high, and the tetrahedron is almost imperceptibly off of the exact. You know, I take that as quite firm confirmation of the convergence.
Okay, and then the other thing, you could make any approximate scheme you came up with satisfy certain rules with, in particular, the high temperature limits.
Yes.
You know, and then I'll go back to I mean, maybe it is just
You could,
cookbook
and-
stuff,
and
but
I
in
should
density
say-
functional theory, it's common to cook things up.
Yeah, so I would say also in terms of this convergence, so I pointed out that that in the CVM there are questions of what is the correct sequence. Like, should we go from a pair to 2 pairs to 3 pairs and so on? No, that turned out to be a bad idea. I showed you that nearest plus next nearest was not a good idea. That's what was here.
Okay.
So the rules for forming the clusters are unclear. As you say, the high temperature series is a way to think about it. There's also a nice paper by Voul and de Fontaine. I don't know the year of it, but Voul, V-U-L, and Didier de Fontaine, who has done a lot of great work on order-disorder transitions. And I cite here, by the way, an really excellent review article of his. A little bit old now, but still quite excellent. They also did some work, and they proposed on the basis of somewhat intuitive notions what the proper sequences were for several interesting lattices.
Yeah, and another aspect is that you're not always interested in pair interactions.
That's right.
And you can, but there should at least be some functional for which the higher order interactions would be, variationally small.
So here is the expression that I use for the entropy. For the energy in the 4-point case. So you see that this allows nearest and next nearest neighbor interactions, 3-point and 4-point. So it includes every interaction that you can identify in here. And it also includes chemical potentials.
Okay, thank you. Enjoyed the talk.
Thank you.
So I'd like to mention that, there is another alternative way to expand systematically around mean field theory, which is one can fix the order parameter by a Lagrange multiplier and then expand the free energy in a cumulant series around this reference system. I don't remember who has or what, I will actually share later on some references on this. I suspect that this is actually closely related to this, but I'm not sure. The reason why I'm mentioning is that this is a method that has been actually used in the context of spin glasses to do 1 over the expansion or something like that. And so I think it kind of automatically calculates things to a certain cluster size. It doesn't, it says automatically how it works. I'm not sure exactly the relationship to this, but I think it's closely related, probably. Maybe that will resolve some ambiguity. But I want to mention another thing. I've actually tried to use this method in my work where I wanted to work on Coulomb interacting systems. But then what I discovered is that what was kind of, I think, first realized in the context of the random phase approximation is that you have long-range interactions, then you cannot stop this cumulative expansion to finite order. You have to get the divergences away. Otherwise, everything blows up. And then one has to resum chain diagrams to infinite order in order to bring in screening at some low elementary level. And this is a technical nuisance because I originally worked with a kind of cluster theory like this, but then when I put on a long-range interaction, then I found that the various cluster terms, they all blow up and they have to be resummed. So that's actually a technical problem. It may not be a problem, I think, for metals or similar systems where we have screening, built in. I mean, basically, the interactions that you're putting in here are already screened by conduction lectures or something like that. But I think for ionic systems, it actually could be a significant thing. And I want to, this is why, that version that I've described in the last meeting, which is very simple, much simpler than this. In fact, it's the lowest order series. You can think of it, this is like a lowest order approximation that can actually treat the long-range interactions in a way that's kind of quantitative. Mm-hmm. And so I guess you probably haven't applied this to long-range systems, right? Or ionic systems.
No, I've not.
Okay. Yeah, that's what.
Yeah, I will say that that there are generalizations of this to liquids. And there are generalizations of this to include vibrational disorder. And so Don has worked on some of these ideas. I will also say, if you want to know more about the formalism, the first place to start is this paper of An, who pointed out the Möbius inversion. And then if you look at papers that cite this, you'll find lots of nice things. And then if you want to go a little more into the computer science side of things, there's a method known as belief propagation that is used in computer science contexts to use known correlations as constraints on trying to solve various kinds of optimization type problems. Let's see. I think his name is a guy named Jonathan Yedidia.
Yes, that's the one name I'm familiar with somehow.
Yeah, belief propagation.
Yedidia. So the nice comparison with Monte Carlo that you've shown, that's in the reference 5, is that right? Or 6?
That is Kim.
7.
That is
yes.
7.
Yes.
Yeah. Yes. And I also want to call out references 8 and 9, who I think have done the best job of applying CVM within the context of high entropy alloys.
Very nice.
Yeah, so the first 4 are kind of foundational papers. 5, 6, and 7 are the most relevant papers of mine. And then 8 and 9 are the best for high entropy alloys.
Does everything stay basically the same with high entropy alloys, or do you have to do any, like, I don't know, unique select, or some, do you have to, like, is there any like question mark about selecting the clusters in that case, or like when you have, very
there's nothing really new. There are questions about how you will determine the terms in the energy expression. So how do you create the interaction model? And then you are also in danger of having some difficulty controlling the concentration. And so you have a choice to make about whether to work as functions of chemical potentials, which I find quite annoying if you really want to know about the equiatomic problem. What are you going to do to keep yourself equiatomic? So that's the biggest problem that you have with the high entropy alloys.
Okay, thank you.
Okay, any other questions? If not, I'm going to stop recording.